Thanks for the introduction. My name is Sergey Kruk. I'm talking about nonlinear imaging of nanoscale topological corner states. This is collaborative research done between universities in Australia, Germany, and UK, the Australian National University, University of Paderborn, and University of Birmingham. My talk will be more on a fundamental aspects of science, fundamental physics, also with some important applications. So the talk is generally about topology. And topology is mathematical discipline, studies certain properties of systems, some global properties that remain unchanged when we continuously tune some system parameters. First, topology was applied to geometry, to geometrical objects. Here we see an example of one object morphing into another, a cup into donut, and vice versa, a donut into a cup, by some continuous stretchings and bendings, some continuous deformations. So topology claims that some global properties of these geometries remain the same despite the geometries looking quite different. And simply speaking, it goes down to a number of holes in these geometries. Both a cup and a donut have one hole, and therefore it is possible to change one into another continuously. For example, however, if you compare a donut to a sphere, and then sphere has no holes, donut has one, and we cannot change one into another by continuous deformations. At some point, we need to pierce a hole, and piercing is not a continuous deformation anymore. So topology characterizes systems with integer numbers, with topological invariance. In geometry, it goes simply down to number of holes, and we can either count those holes to figure out what the topological invariant is, or we can apply certain mathematical procedures. We can calculate certain surface integrals that will yield us these integer numbers. Perhaps for simple geometries, it might be not worth employing some complicated math. But if you go to just a little bit more complicated geometries, like for example, two figures here, it might already not be completely obvious from the very beginning whether these figures are topologically the same or they're topologically different. Or in other words, if one figure can be obtained from another by some continuous stretchings and bendings. So with this example, we can perhaps do a mental exercise and figure out that yes, there is a topological equivalence. One figure can be obtained from another by continuous stretchings and bendings. But at this level of complexity, we might already opt out for some mathematical tools to calculate surface integrals that yield topological invariance for us. More recently, topology was applied to physics, first to electronic systems, and later on to photonic systems or to optical systems. So here we consider the entire Hamiltonian of a system, or we consider, let's say, the entire energy spectrum of the system. And we apply certain procedures, conceptually similar to surface integrals, and we attribute integer numbers to these systems. And these integer numbers are topological invariants. And these integer numbers remain the same as we change many system parameters. And interesting physics happens when we bring two topologically different materials together. So as long as we have a boundary, a domain wall, between two materials with different topological invariants, these boundaries might host new physical states. In electronics, that would be new states for electrons, let's say new conductive states. In optics and photonics, that would be new states for photons. So new optical modes, either propagating modes, waveguiding modes, or localized modes, let's say cavity modes. And what's interesting about those modes is that their origin comes from the properties of the entire system, from the properties of the bulk. It does not depend on exact details of the boundary itself. So going to earlier example of changing donut into a cup and not changing topological properties. In this case, we can do a lot of changes to the boundary, make sharp corners, introduce defects, and the topological properties will remain, which means topological modes will be preserved. So in this example here, a topological mode is a waveguiding mode, so it propagates along a domain wall of two materials with different topology. And here it is an example of a rather huge defect being introduced. and the mode nonetheless keeps propagating forward no matter what. So this is the form of topological protection for optical and photonic systems such as waveguides and cavities. And recently we've done some research on optical systems, nanoscale sub-wavelength optical structures which have non-trivial topology. Here I show example of few classes of such structures. The simplest example is just a one-dimensional structure which hosts localized states at the corner. So if you like, one-dimensional structure with 0D states, as well as an example of a 2D structure with 1D topological states. So 1D waveguiding modes, as well as a 2D structure with 0D states. Localized cavity modes at the corners of the domain walls. And the two latter examples were done with the help of non-fabrication facilities at the ANFF ACT node. So I will focus more on those. So how the structures look like? These are nanoscale samples made of silicon nanostructures on a metallic substrate in this case. So structures consist of two types of unit cells. These are silicon pillars arranged into hexamers. And we have slightly shrunken hexamers where pillars are pushed a little bit closer to the center, and expanded hexamers where pillars are pulled a little bit further from the center. And then arrays of such hexamers, shrunken and expanded, happen to have different topological invariants. And the domain wall between these two lattices gives rise to new interesting optical states. So in terms of Australian National Fabrication Facilities, this fabrication involved electron beam deposition of metals, chemical vapor deposition of thin film of silicon, electron beam lithography that was defining the pattern, and all techniques that come with it, such as spin coating, wet chemistry, and then the electron beam lithography pattern was translated into silicon using reactive ion etching. The fabrication here was done by Professor Duk Choi, who is also with us today and who will be the speaker in this session a little bit later, talking about different research. So these structures host many optical modes. On this plot here, we show calculations of eigenmodes of the system. So every dot here is a particular optical mode that sits inside the structure at different frequencies. And these are colored in black, blue, and red. And black modes are bulk modes, so they exist in a two-dimensional volume of the structure. One example shown here, it's an experimental image of light distribution within this structure. Blue modes propagate along the domain wall, and an example shown here. So these are some sort of waveguiding modes along the domains between two topologically dissimilar structures. And one very special red mode shown here in this mini band gap is a corner state sitting at this corner of the domain wall. If you have a closer look, we have two examples of topologically non-trivial structures that support corner states, and we contrast them to a very similar structure, but which is topologically trivial and does not have this special state at the corner. And we see that the topology, this rather abstract concept, bring very clear real-world observations of nice and tight light localizations. And we confirm that these are robust against many perturbations of the system, including some fabrication imperfections. And essentially here light is localized within a single unit cell, where the whole unit cell is smaller than the wavelengths of light. So we localize light in a sub-wavelength volume with a degree of topological protection. So to conclude my talk, we designed and fabricated two-dimensional topological insulators that host 1D modes and 0D modes, or let's say waveguiding modes and cavity modes. And these modes are protected against many perturbations and fabrication defects by topology. And we generally believe that nanoscale topologically protected waveguides and cavities might find applications in on-chip compact photonic devices, both classical and quantum devices. With this, I would like to acknowledge our funding agencies and give special thanks to Australian National Fabrication Facility, ACT node. Thank you for your attention.
Sergey, we have one question from Michael Stuiber. How is the topology created? Do you create an inverted band structure at the silicon aluminum interface?
So how topology is created? Basically, each unit cell here is a resonator hosting different modes, either electric dipole mode or electric quadrupolar mode. And then topology comes through the existence of those modes and and interactions between them. More specifically, it yields non-trivial spin chair numbers, so spin chair numbers other than 0. And regarding the presence of metal, then yes, conceptually what is happening, the structures are effectively standing on a mirror, so they reflect themselves. And this reflection first effectively doubles their length, which is useful from a practicality point of view, from fabrication practicality, but also this reflection enhances symmetric modes and it suppresses anti-symmetric modes, which comes handy for this particular design.
Thank you.